What the heck would I know about celestial navigation, right? In college, I was an art major. Professionally, I'm a designer and a web developer. I know some basic concepts, but I've never even been on a boat in open ocean before, let alone formally trained in navigation. That's why I never made a video like this before. I figured I'd better leave it to the bigger science channels or the real pilots and captains. But then I learned a few more tidbits, and I heard about yet another flat earther covering the topic badly, and I knew it would be good if I could speak more knowledgeably on it. And then I felt the magnetism. Do you know what I mean by magnetism? That feeling like a tingling in the brain when enough puzzle pieces are close enough to fitting that they start to tremble and lean toward a sensed solution. It's when I can tell that a light bulb moment becomes possible with just a little bit of concentrated thought. There is a learning breakthrough within reach. So I thought, if I document my learning breakthrough for all of you, maybe it would help someone. To experts, I'm sure this will seem sloppy and underdeveloped. And to some lay people, I may not be able to cover enough earlier puzzle pieces to make this accessible for you, but I will try, and I hope that you do find it helpful. One crucial piece of the puzzle that I've had for a long time, but that many people lack, is the concept of a celestial sphere. According to modern science, the closest celestial object in our sky, our own moon, is 240,000 miles away. By astronomical standards, that distance is absolutely minuscule. But to us, it is so far away that from one side of the Earth to the other, there is barely any parallax. That is to say, at any given moment for two earthly observers, the moon's angle and position relative to the stars do not change much. Almost as though it's painted on a very distant background. And the more distant something is, the more that concept applies. Our sun is 93 million miles away, so almost 400 times farther than the moon. And whatever tiny amount of parallax we see on the moon, there's only 1/4% that amount on the sun. Once we leave the solar system, there's a huge gap in scale until we reach the next closest star system, the home of Proxima Centauri. Here, miles and kilometers become kind of useless as units of measure because you have to add so many zeros. You could say it's 17 trillion miles away from Earth, or you could just say 4.25 light years. Whichever you choose, that is a long way away. And that is the nighttime star that is closest to us in the entire universe. That's our galactic front doorstep. Beyond that, the zeros keep piling up fast. And the next huge gap in scale is when we leave the galaxy. Stuff beyond this, astrophotographers refer to as deep sky objects, and they are in the billions of light years away. If these numbers break your mind, don't worry, you're not alone. God made the universe big, I believe, as a testament to his greatness. Because he is so big and powerful, if we beheld his full glory, he would break our minds in the same way. To him, the night sky is just his little art gallery that he put outside our window, because that's just the kind of God he is. So what does all this mean for celestial navigation? Well, it means that when we observe objects in space, the entire concept of parallax becomes almost negligible. Let that sink in for a moment, because that is dramatically different from what we're used to in everyday life. Video games can actually help us out here. In the old days, 2D games had certain tricks to give an illusion of depth. As you moved through the level, different background layers would move different amounts to mimic parallax. The farthest background layers would obviously move the least. And if the game designers wanted it to seem very far away, the deepest background layer would be fixed, it wouldn't move at all. If the distances become great enough, parallax just doesn't apply anymore. Sound familiar? In more modern 3D games, there's something called a skybox. The reason it's called a box is because of implementation details about camera projection and perspective, but it's basically a layer of scenery rendered behind all the other scenery that does not move in relation to the camera. This removal of parallax instantly gives the illusion of limitless distance. This is, or at least was, a popular tool for game designers because the illusion is so effective and so dirt cheap to make. All you have to do is treat camera translation as 0 and boom, instant skybox. You see, the inverse correlation between parallax and distance is a defining trait of how we see the world. And almost all of space is off the charts on one side of that inverse correlation. You can think of it like the rest of the universe is in our skybox. In ancient times, astronomers thought this was literally true. They believed the heavens were a series of concentric spherical shells revolving around Earth. They called these the celestial sphere, and this concept is still extremely useful in describing our earthly vantage point in the universe. The geometry still works for exactly the same reason that a video game skybox works. To the eye, there's almost no difference. For this reason, in astronomy, it's very helpful to think in terms of a celestial sphere. Astronomers specify locations on this sphere using a spherical coordinate system aligned to Earth's equator and axis of rotation. If we look at north as the top, then the up and down coordinate is called declination, and the left and right coordinate is called right ascension. But of course, this is usually layered on top of our earthly orientation, where up for us is the zenith of our sky, and because Earth is a sphere, this will differ from celestial north depending on our latitude and longitude. That's why astrophotographers often put their telescopes on a special mount called an equatorial mount that lets them factor out this terrestrial orientation and more easily match sky movement with their telescope. They can do this anywhere on Earth with just a simple angular adjustment because remember, across the surface of the Earth, parallax in the night sky is not really a factor. All that matters is rotation, not translation. Even though up and down are defined differently for every region on Earth, every astronomer in the world who is using an equatorial mount right now has it oriented the exact same way, along Earth's axis. If you are following this far, then hopefully you see why a 24-hour sun in Antarctica makes perfect sense on a spherical Earth. On any given day, the sun makes the exact same small circle path on our celestial sphere for all observers on Earth, or great circle path if it's an equinox. The difference between me and the TFE crew in Antarctica was nothing but orientation. On the celestial sphere, the sun's path was shaped exactly the same for me and them. As they traveled south, their translation made no difference, but they were slowly rotating their celestial sphere.
Sometimes you are wrong in life. The sun does circle you in the south. So what does that mean? You guys are going to have to figure that out yourself.
Jaren, it means that relative to me, you were standing nearly upside down, which put the sun's small circle path entirely above your horizon. That's what it means. So, the orientation of the celestial sphere around us is directly correlated to both time and our location on Earth, and the basic geometry of that is something that astronomers have known for thousands of years. One really lovely simplifying fact about astronomy is that objects outside the solar system are very nearly fixed in place. Their motion takes centuries to become casually noticeable, rather than days or months like the planets. Considering this and the aforementioned correlation between location and orientation, it makes sense that you could work that back the other way. If you know the time and you can measure how the stars are situated above you, then you can calculate what latitude and longitude on Earth would be required for the celestial sphere to be oriented that way. I learned this part from a Bob the Science Guy video on May 2nd called What Does a Sextant Measure? You find the geographical position of a star, that is the point on the Earth where the star would be at the zenith, and the star's angular difference from your zenith gives you your angular difference from that point along the surface of the Earth. Do that with 3 or more stars, and you'll have 3 or more circles intersecting somewhere near a single point, your location. This process is called trilateration, where you use its distance from 3 or more data points to find a 4th point. We use this same mathematical process to find the epicenter of earthquakes, and your ears use something like it to locate sound. Ultimately, it's the same process that GPS uses. Now, the part that was still magic to me until recently was how to know a star's geographical position, or substellar point. I knew there were catalogs and almanacs, and I knew there was math involved, and somehow it worked. I didn't look into it. Too busy, not curious enough. Also, I think I glanced at this Wikipedia page, and all these charts and this complex trig honestly scared me off. But the really fun thing was that recently, when I became curious enough and started to think about it on my own, glancing at this article again only to confirm certain details that I wanted and frankly ignoring the scary trig, I realized I had almost all the right pieces already. And it was maybe, just maybe, way simpler than I feared. And that's when I felt the magnetism. Before I share that, there's a few more rote facts that I need to skim through quickly. A lot of this is just special terminology for familiar things, so hopefully you can keep up. To start with, the Earth spins once a day on its axis and orbits the Sun once a year, right? Right. The axis is tilted 23 degrees from the orbital plane. Both motions are counterclockwise when viewed from celestial north, because the sun rises in the east, right? So relative to the sun, the surface of the Earth has to scroll to the east. The 2 points along Earth's orbit, where the axis is perpendicular to the sunlight, are equinoxes. After the March equinox, the North Pole faces more toward the sun, and after the September equinox, the South Pole faces more toward the sun. On the celestial sphere, the orbital plane is called the ecliptic, because by definition, an eclipse can only happen when a third body intersects this plane between Earth and Sun, so that is always where eclipses happen. Throughout the year, the sun follows the ecliptic toward the east, because Earth's spin is prograde, remember, same direction as its orbit, and if you picture that, trust me, the sun moves toward the east relative to the stars throughout the year. But throughout a day, everything, including the ecliptic itself, turns on the axis toward the west, and the orthodrome perpendicular to this axis is, of course, the equatorial plane. Declination is simple, an object's angle above or below the equatorial plane. It's pretty much exactly like latitude. Right ascension is longitude, but in relation to the fixed stars instead of the surface of the Earth, specifically with an increasing angle measured east from this point right here. Why? Because if you stand on the equator at the March equinox, then this point in the sky rises with the sun, or ascends at a right angle to the horizon, hence right ascension. Because of this reference system, it's often measured in time at 15 degrees per hour instead of in degrees. In astronomy, you'll hear a lot of terms like that which conflate time with east-west angle, often ending in the phrase hour angle, like hours on a clock. 360 degrees is 24 hours. Oh, and this point at a right ascension of 0 is also called the first point of Aries, or in almanacs just Aries for short, or even just this symbol. So that's the jargon. There's a few related terms we will use, like Greenwich hour angle or GHA for a star's angle from Earth's prime meridian running through Greenwich, England, or SHA, sidereal hour angle, which is basically right ascension but measured the other way. And one more tidbit. In a star catalog or encyclopedia, if you look up a star, you can usually find its equatorial coordinates, that is, its declination and either right ascension or sidereal hour angle. Now, due to precession of equinoxes over the centuries, as well as the motion of the star itself, called proper motion, these coordinates will differ very slightly depending on when they are measured. Wikipedia gives them for the January 2000 epoch in relation to that year's equinox, but something like Stellarium, or a periodic publication like an almanac, can give much more current numbers. Now, there's something else really beautiful about astronomy. All that messy complexity about proper motion and epochs is only needed if you want scientific precision. You would want that if you were actually at sea with your life depending on accurate navigation from this method. But look at these two numbers, from Wikipedia at the January 2000 epoch, and from this nautical almanac for today's date. Converted to the same units, after a quarter of a century, they are only a handful of arc minutes different. So if you are not doing real science, but just trying to learn the basics, you don't have to know any of that. You could use any measure of a star's right ascension and declination because it will stay roughly correct for centuries. A basic element of science, which flat earthers constantly and stubbornly fail at, is to discern what factors in a situation will have a large impact on your results and what factors will have a small impact, perhaps even negligible, and being able to quantify what negligible means for your particular purpose. For our purposes in this video, the difference between a star's coordinates at an epoch versus the current date are going to be negligible. Frankly, I'll be happy if we can get a location fix within 100 miles. Okay, are you still with us? I sure hope so, because this is about to get really fun. I've just knowledge dumped to you everything I had, and a little more in fact, when I felt the imminent learning breakthrough. All the pieces are there. Do you sense it? When I sense that, I feel the need to slow my world down, to shut out distractions, go to a place of mental abstraction, and just picture the problem. It's right there. Declination is latitude. We are ignoring oblateness of Earth and any other possible deviance. The star's longitude, that is a tad more complicated, but not out of reach. On the March equinox, it's relatively simple. A star with right ascension of 0 will be at 90 degrees east, rising at that moment for any observer on the prime meridian. In fact, all three of these factors, time of day, time of year, and star's right ascension, contribute in exactly equal proportions to the star's longitude, and all the motion is linear through time. This geometry problem is not trig, it's arithmetic. UTC is measured from midnight, so at 0 UTC, on the March equinox, the first point of Aries will be opposite the prime meridian over the international dateline, or let's say 180 degrees east. From there, adding hours in the day winds it westward. Adding degrees of right ascension winds it back eastward. Which way does time of year wind it? Well, since the Earth's spin is prograde, that means that as the celestial sphere spins, the fixed stars spin just a little teeny bit faster than the sun, leaving it behind at a mean rate of 30 degrees per month. That's 1/12 of a turn per month, or one full turn in a year. And UTC is based on mean solar time, so it stays in sync with the sun, not the stars. It's synodic, not sidereal. So if we imagine ourselves synchronized with the sun, then throughout the year, the stars are advancing westward. So if that term in the equation is positive along with time of day, while the right ascension is negative, then the final result is in degrees west. And remember, we need to shift by 180 degrees because right ascension of 0 starts out opposite the prime meridian where the longitude of 0 is. A good way to figure 30 degrees per month is by the day. So take the current day of the year, subtract the March equinox, divide by 365.2422, and you have fractions of a turn. From here, you could either multiply by 12 to get fractional months and then by 30 to get degrees, or you could just multiply by 360 to go straight to degrees. As soon as I thought of this formula, I brought it to Danny Faulkner, who is a professional astronomer, and I asked him if it seemed accurate. In my message here, you can see me bracing to be wrong, because I was still worried about all that scary trig I'd seen on Wikipedia. My formula was way too simple, it had to be wrong. And yet, at the same time, I knew it couldn't be wrong. And it wasn't. It was different, very slightly, from the one Danny Faulkner gave, but my formula was giving correct answers. He preferred to look up something he called sidereal time using an outside resource, and it turns out my formula was basically a way of calculating this sidereal time from UTC and the calendar date. I also looked up the same stars we were looking at in this nautical almanac, which was giving Greenwich hour angle for Aries. Danny said this was another way of describing sidereal time. And this too matched my numbers. So what was all that scary trig? Currently I'm thinking it's for an analytic approach to the next step in celestial navigation, which is taking the substellar points that we just found and finding the circles of equal altitude around them on some given map projection. So basically the trilateration step. For this video, I'm not worried about all that, because for that step, I have an arts and crafts approach. First, let's get some actual measurements. But here's where I have to apologize. My wife and I are currently traveling with some of our belongings in a storage unit in another state. That includes my good sextant. This one is a beautiful desk ornament, but well, it's what I've got right now. It'll have to do. Furthermore, I am very far inland and do not have a clear view of any horizon, which means to measure the elevation angle of a star, I need what's called an artificial horizon. There are way better tools and techniques for this, none of which I can really employ in my current situation. So I am trying not to be embarrassed at how sloppy I had to be on this part. What you need to know is that an elevation angle is measured relative to eye level. That is the basic concept, and that is why I'm trying to use a spirit level on my sextant. This technique worked way better when I had a table to set it on in my sunset experiment 5.5 years ago. I also made sure to pick stars from this list of 57 navigational stars, which are easier to find in almanacs. I chose Betelgeuse, Capella, and Marcab, and here are the results I got. I used Stellarium to help me identify the stars and to roughly sanity check my results, but these numbers came exclusively from my sextant. Here are their celestial coordinates according to the almanac. Using my formula, I calculated the longitudes for their substellar points, which I will mark with pins on this globe. Oh shoot, this is one of those decorative globes too. Did I mention my stuff is in a storage unit? I've heard flat earthers whine about seeing this on globes. For decorative indoor use only. But this is genuinely the first time I've ever seen what they were talking about. Guys, all you have to do is buy a real educational globe. It's not that hard. If you look closely, you can even see the lack of manufacturing precision. I just knew the difference was not that important for this video. To find the substellar points, we have to actually measure, and the first thing to do for that is to figure out the scale of this globe. On a real educational globe, the scale would be listed. We're going real sloppy today. Make sure it follows the equator all the way around so we don't get a small circle measurement. We need a great circle / orthodrome measurement, and we are at 40.1 centimeters for the circumference. Started out with these numbers, the latitude and longitude, along with the zenith angle that I measured for each one. What I needed to do was convert those degrees into centimeters on this tape measure, because that's what I'm using to measure the globe. And this tape measure only shows millimeters, so I don't really need more than 2 decimal digits of a centimeter, because I can't use it anyway. Measured a circumference of 40.1 centimeters. That was my conversion factor. And I converted all the numbers to centimeters. And that's what I'm going to use to mark the substellar points on this globe with this tape measure. Longitude, we have to do the longitude first because if we do the latitude first, that changes the length of a degree of longitude if we're not on the equator. This measure for the length of longitude is only valid on the equator. 3 millimeters. And there we go. That's Betelgeuse. That's Capella's substellar point. Now for Marcab. There is Marcab. So these are the substellar points of the stars that I measured. For the radii for the circles of equal altitude, taken from the zenith angles. Now, here is where a drafting compass would really come in handy. And voila! We have just used celestial navigation to determine that I am somewhere in the southeastern United States, somewhere in or around the region marked by these 3 intersecting arcs. I consider that a major win, not because of the precision. This is a few hundred miles of error, whereas Bob the Science Guy said he could get it within 2 nautical miles. But because this shows that I have the concepts correct. This is accurate, even if it's not precise. I bet if I used a better sextant with artificial horizon and a bigger, more accurate globe with real drafting equipment, I could probably tighten this up to within a few dozen miles. Only then would my limiting factor be likely computational from all my simplifying assumptions. Most flat earthers can't even get through this conversation. To them, the flat horizon is a religious icon. So if they even think of a straight line that to them resembles flatness, like a tangent to the Earth's curving surface, then they instantly shut down the conversation in an irrational victory seizure, thinking they just won because you mentioned a straight line.
Welcome to Flat Earth.
Yeah, that's the thing. But for those of you who are not too far gone, I hope this helped you see how celestial navigation not only works on a globe, but absolutely proves a globe, because the math is defined by the shape. If the shape were wrong, then the math would be wrong, and ships all through the ages would not have been capable of navigating by this method. Thank you so much for watching. See you around.